Hi and welcome to another lecture on Calculus 2. Today we are going to talk about improper integrals. Let's go take a look at this topic. Okay, what are improper integrals? In calculus, you start with the concept of integral in calculus 1, where you are calculating something that you write is integral from a to b of f of x dx. Do you remember what that represented? You had a function defined on the real number line, so perhaps something like this, and the function was a continuous function. Then you start from some location a to some location b, specific locations, and you aim for the area between these four walls here. That is what you are calculating. So the integral, or area A, refers to this area. If you wish, we could call that a proper integral, even though the terminology doesn't get to be used. It's just called an integral or definite integral. Now what we are going to take a look at is, what if this starting point is all the way to the left? What if I start at minus infinity and calculate the area? What if this right point is all the way to plus infinity? What if both, that a is at minus infinity and b is also at plus infinity? Those are some categories of so-called improper integrals. So if either a or b become infinite, or if both of them are infinite, then we are dealing with an improper integral. So one type is starting from minus infinity and coming to some location. Another one is starting at some location and going to plus infinity. Still, a third possibility is starting from minus infinity and going all the way to plus infinity. So if either of these two endpoints are infinite, we are dealing with an improper integral. So to draw a picture that perhaps brings this issue home, suppose we have a curve like this. That's the curve of the elephant that swallowed a snake that swallowed an elephant. At any rate, what if I start at this location and I want to go all the way to infinity? I want to calculate what this area is. My stopping point B has just gone all the way to the right. How about starting at somewhere here? Let me draw another picture so things don't get mixed up. So this is going to be a representation of a to plus infinity. This is your function f of x dx. We are looking at calculating this yellow area. How about the other category? Suppose I have, let me draw something similar to that again, and suppose I have this point and call that b, and now I am looking at this picture. I'm trying to calculate this area. How would I go about doing that? So that is the integral. Now from minus infinity means I'm going all the way to the left. Minus infinity, I stop at b, and then I have f of x dx. Perhaps I go all the way, say, okay, I want to actually go all the way from the left to all the way to the right, and now I want to calculate all of this. So that's the picture of the third type. I have from minus infinity to plus infinity of f of x dx. So this is one type of improper integral if your limits are infinite. The second type of improper integral is when the function itself has an infinite limit in the area that you're looking at. So the a and b could be any of these, and or it could be just from a location to another location, both of these things finite. But now we are facing another obstacle. What if the function explodes to infinity? So suppose I have something like this. A function goes all the way to plus infinity, and whatever it does on the other side, perhaps it comes all the way down like this. And then you want to go still from A to B, and somewhere here you have that so-called asymptote. The function has gone to infinity, and then you still want to figure out what this area is going to be. And on top of that, the A and B themselves could have gone to infinity. So there's all sorts of things that could happen. A typical problem just focuses on one item going to infinity, just so that we don't combine too many things all at the same time. But in principle, everything could be combined. So this type of problems, you typically look at the situation where perhaps you have a function a that comes to some asymptote like here, and it's approaching either going to plus infinity or minus infinity, and you are trying to figure out what this area is. And in this situation, the idea is that limit of f of x as x approaches c. Here's my point C, and as I approach to this point from the left hand side, in this picture I go to plus infinity. I could have gone to minus infinity, perhaps I could have approached from right hand side, but here's a possibility. And the question now is, well, in this situation, if I want to calculate the integral from a to c of f of the x dx, how would I make sense of it? So none of these cases are covered by what you studied in calculus 1. That is not a subset of that definition of a so-called Riemann integral you had there, and we have to have some additional notations and definitions for making sense of any of these things. So I'll go ahead and talk about some of these things. You can infer the other possibilities from a few cases that I will do. So maybe I do one case like this, and this one will be similar to that. Just instead of plus infinity, you have minus infinity here. A problem like this, well, you split the problem at any place you want, and you do a left integral like this blue type and a right integral like this yellow type, and then add them to each other. If you have several infinities in your function, again, you break it up and do it piece by piece, and then you just add them up. You see that the main prerequisite for this section is the knowledge of limits from calculus 1. You need to be good at that, figuring out the limits of things. And in particular, there was one technique that was very helpful. That was L'Hopital's approach for finding limits. So we are going to liberally make use of all of those topics, and you need to go back and take a look at Cal 1 to refresh your mind about these things. So let's just do a few examples. Now there are some definitions in any textbook you see. How do we define these things? So for example, if I want to calculate integral from a to infinity of f of x dx, how do we actually formally define it? If you want to formally define it, integral from a to infinity, what do we mean by that? What we mean is that, well, stop at some temporary location, call this temporary location B, find the area up to that, so find this area, and then start pushing B toward the right. As you go one step and another step and another step, And in each case, figure out what the area is going to be and find the limit of that as b goes to infinity. So that is the definition. We need the operational definition of what do we mean by integral to infinity. And the definition is, well, go to from a to b, just like what you did in Cal 1, and then after you have done that, then let b go to plus infinity. This is for plus infinity case. So that's the definition for what this limit means. And all the other cases are defined in a similar style. I let you read your textbook. It's just as readable as it could be. So all the other cases, you might challenge yourself. How would you write this one? If I have integral from minus infinity to whatever you want here, let's call it b, f of x dx. If I want to define this in this style, how would I do it? How do I use the concept of limit to make this definition? So just take a minute to come up with that definition, and so you pause this thing and you try to do it yourself. So what do? We say, well, stop. Let's come to this picture. I want to have a definition for this entire tail. How do I do it? Well, stop somewhere, call that A. Figure out what the area is going to be. That's from calculus 1, from A to B. And then start marching toward the left. Come to here and see what the area is going to be. Further to left, further to the left. So what are you doing? Marching toward minus infinity. And at the end, what you are going to have is the limit that you are after. So here, from A to B, you go calculate it just like you did back in Cal 1, and then you take a limit. What limit? What should I do to A? We said we have to send A to minus infinity, and so on. So in this case, you just break your problem into two parts and deal with each of them separately. And let's do an example of this problem as well. How would you think we are going to do that? Well, if this is going to infinity and it wreaks havoc with your Riemann integral, what you do is that you stop short of it. So you stop short of it, maybe call this one point B. So we are going to define this thing as the limit of integral. So you go from A to B. Well, there's no problem from A to B. Nothing is infinite. So our calculus knowledge is going to help us hopefully figure out what this integral is. And then what? And then we say let B go toward this wall, and let's see what happens. So we let B to go to C, and since I'm coming from the left side, well, we do it like that so that we stay on one side of the infinity, and so on. So the definition is rather straightforward. You want to practice, convince yourself why the definition looks the way it does, and let's do some basic problems. What are some of the basic problems? Well, here's one of the very basic ones. 1 over x squared dx, say from 1 to infinity. A function that comes up in many applications. 1 over x squared. So what does 1 over x squared look like? Well, it doesn't have a name or anything. It doesn't have some major properties, but just looks something like this. Deceptively looking like a hyperbola, but it's not a hyperbola. So this is a graph of 1 over x squared. What are we planning to do? We're planning to start at 1 and go all the way towards infinity. So what we want to do is to calculate this area. What was our plan? The plan was to cut this thing short, stop at some b, and then send this wall at b, send that to infinity. So the definition was the limit of integral from 1 to b of 1 over x squared dx, and now you're letting b go to infinity. So Now the problem is resting on the shoulder of this. So we need to figure out 1 to b of dx over x squared. That's a very basic integral. Let's write it in power notation, x to the power of minus 2 dx. Let's just remind ourselves we need our basic formulas. U to the power of n du. What was that? Do you remember? U to the power of n plus 1 over n plus 1 and plus a constant. Yeah, so long as n was not minus 1. So our antiderivative, the exponent, we increase it, we divide by the new exponent we have, and then remember in definite integrals, if this was from a to b, then you have to calculate this thing from a to b as well. So I have to take this thing and calculate it from 1 to b. Let's write this thing in a nice way. So this becomes x to the power of minus 1, which means 1 over x, and this is minus 1, which I might write it here. So 1 to b. So plug the b in this, minus 1 over b, minus plug 1 in this, minus 1 over 1, or to clean up 1 minus 1 over b. Now what? Now we said we let b to go to infinity. So I let b to go to infinity on this, from 1 to b of d of x over x squared. Well, that is what this integral is. So I'm taking limit of 1 minus 1 over b, and I'm letting b to go to infinity. So in this case, we don't have any problem figuring out what the limit is going to be. So it's not a challenging problem. 1 over infinity is 0, and the limit turns out to be 1. So we need to be able to calculate the limit. In this case, it was obvious. Some other cases you might have to use L'Hopital rule or whatever other techniques you learned in calculus 1 for doing this. So what we have learned is that total area under this curve is 1. So it's as if you were going to paint all of this, the amount of paint that you use, you want to calculate it. This is as an indicator of how much paint you need to go all the way to infinity. Due to the fact that this is thinning out, the amount of paint that you use is staying finite. Okay. If the answer that we get is a number, we say the original improper integral was convergent. So we say this integral from 1 over b of dx over x squared is a convergent improper integral. Okay, excuse me, I'm supposed to replace the original problem we're talking about. The integral from 1 to infinity of dx over x squared is convergent. No, what's the opposite of that? Opposite would be divergent, which means what? It means when you want to take a limit, you don't arrive at any specific number. Let's take an example of that, a very famous case of an improper integral that doesn't give us a finite number, and that's the following: integral from 1 to infinity of 1 over x dx. What is that? Well, again, we start with limit from 1 to b of that integrand. We have to let b to go to infinity. Well, this is a very famous integral. That's just logarithm of x, is that right? Or logarithm of absolute value of x. In this case, our numbers are all positive, so really I needed to have that. And then from 1 to b, and then a limit is supposed to be taken. So if you wish, calculate the integral first and then apply the limit at the very end. Either way. So now I am combining both steps. we said b is positive, b is going to plus infinity, has to be positive, so it becomes logarithm of b. At 1 I have logarithm of 1. Well, logarithm of 1, that's easy, that's 0. What is left? Limit of logarithm of b as b goes to infinity. Well, what is that? We need to remember limit at infinity from calculus. So here let's do a quick review. What the logarithm look like? Logarithm had a graph looking like this. It starts from positive side, at the 1 it crosses over, and then has a very slow upward increase. However, it does increase, it goes to infinity. As you keep going, this is going to go higher up, and in that case you write in the limit as infinity. If one of these improper integrals you calculate it and you get infinity or anything other than a number, then you are going to call that a divergent improper integral. So this is, if the question was is this convergent or divergent, 1 over x dx is a divergent improper integral. So in these two cases we could easily say what is the diagnosis. Is it convergent or divergent? Later on this becomes a rather sticky point. How do you decide? Here we could easily find the integral, and then our verdict is right in front of our eyes. It's not going to be all that straightforward in all the cases. So we had these two cases. Of course there are many other cases we could consider, like for example find out so the question might be evaluate. Now let's do a case where we have infinity on both ends, from minus infinity to plus infinity of, say, exponential of x over 1 plus exponential of 2x dx. Okay, this you go and graph it. It's gonna look like this kind of picture. Let me show you a quick way of doing this so that you have something to work on. Let's go and let me open my Desmos and well, Desmos calculator. I'm gonna have exponential of x over, I go to the right, then over 1 plus exponential of, when I go on right exponent is shift 6, of course, 2x. So that is, let's blow it up a little bit so that we see how it looks like. Or sometimes you can change the scale to make the picture stand out a little bit better. So here I don't want much on the negative side, so minus 0.2 is good enough, and let's stretch it up here. So I want to be here's 1, for example. So that's how the picture looks like. We are trying to find the area under this thing, but okay, so I zoomed out now. You see at the end the tail is flattening out, and flattening out rather quickly, and we want to know what's the total area under this. So there are two possibilities. If the total area is infinite, that means the integral did not converge. If the area turns out to be a number, then we say it's a convergent integral. So convergent versus divergent. Now let's see what is the story. So in this software we cannot tell really, it's not easy to tell from a picture which one it's going to be. What do we do? Well, when you have infinity, you might as well break your integral into two pieces. So with this, you find a judicious choice on where to break it. So we need a break point. In this situation, with a symmetric picture like this, we might as well split it at 0. We could have chosen anything, but here is one way to go about it: e to the x over 1 plus e to the 2x dx, and 0 to infinity of exponential of x over 1 plus e to the 2x dx. Now, several ways of approaching this. You might want to show by a change of variable that this integral is going to be same as that integral because of a symmetry that we are looking at, and so on. But here let me just pick on one side of this one. Integral from e to the x, integral from 0 to infinity of e to the x over 1 plus exponential of 2x. So as soon as we split it, then each of these is going to be like the kind of problem we have done, like from a number to infinity. So it's going to be that kind of a limit. So this is also same thing, limit from 0 to b of exponential, same formula. So after a while you want to just do these things rather quickly. B going to infinity. Well, how do we do this? You might remember from the previous examples that you have done, but let's say you don't remember it. Let's just do this thing from scratch. Exponential of x. So we throw away all this portion. So we do away with the clutter. Let's just focus on the integral itself. Let's see what can we say about this thing. So this is one of those basic integrals you see in calculus 1 with a u sub. You can handle this thing quickly. So what's my u sub? If you remember, is exponential of x, and of course du is going to be exponential of x dx, and therefore this integral is simply du over what's in my denominator. Well, if this is e to the x, you square this and the exponent doubles. Is that right? ux is exponential of x squared, and what do you do with the two exponents? You multiply them. So this is u squared, 1 plus u squared. Well, this is a basic integral in Cal 1. It's tangent inverse of u and a constant. Well, that's going to be tangent inverse of exponential of x plus a constant. So in this case, I have tangent inverse of exponential of x from 0 to b, and then I have to take the limit of that. So I put the b in this thing, so I will have the limit of b going to infinity of tangent inverse of exponential of b minus tangent inverse of exponential of 0. Well, tangent inverse in b is the exponent of this exponential. So when b goes to infinity, exponential of b of course goes to infinity. What's tangent inverse of infinity? Okay, we need to remember that from trigonometry. How about here? Tangent inverse of, there's no b here, it's just 0. Exponential of 0 is 1. So that is tangent inverse of exponential of 0. We said it's 1 is 1. Now we need to remember some basic facts from trig. What was tan inverse of infinity? Okay, Hopefully you remember that. That is pi over 2. Pi over 2, tangent of that is infinity. Tangent inverse of 1 now, what was that? Well, that was pi over 4. You subtract these two, you get pi over 4. In the similar style, you show that the other integral from minus infinity to 0 of the same thing, exponential of x over 1 plus exponential of 2x dx, that also turns out to be same quantity. The picture is symmetric. So if I want to figure out from minus infinity to plus infinity what this integral is going to be, I'm going to add the two components. The right component is pi over 4, the left component is also pi over 4, and I am adding these two, and of course my total is going to be pi over 2. That is the case for this integral. It becomes pi over 2. Now let's go ahead, take a look at the other type of integral we were talking about, improper integrals. We said sometimes it's the function that goes to infinity. So the examples that I had so far, we did one example like this, we did another example of this type, has to be broken into these two styles. Now let's go ahead and take a look at something of this nature. We are going to pretty much all the time focus on going all the way up to the asymptote, and or starting from asymptote and going somewhere, as opposed to crossing it just to keep the problem simple. Ideas is all the same. So suppose the question is find or evaluate integral from 0 to say 1 of say dx over, now here I might have anything like say square root of x. Why is this an improper integral? Because if you look at the integrand 1 over radical x and graph it on the interval from 0 to 1, so here's my quick graph. Here is my quick graph of this thing. 1 over radical x again is not a well-known function or anything, it's just some function. At 1, this is 1. As I go towards 0, suppose I go to 0.01 here. Square root of that is 0.1. 1 over 0.1 will be 10, meaning as I approach towards 0, I am pulling up. I'll go all the way to infinity like this. Obviously, when x goes towards 0, denominator becomes 0, positive 0, and fraction becomes infinity. What are we after? We are wondering if this integral, if this area is finite, and if it is, well, what number? And if it is not finite, well, what's the reason for that? What has happened there for it to become infinite? So that is the major question. How do we approach it? We said the idea is to cut it short, like we start at this point b as opposed to 0, and then go ahead and calculate this integral. Once it is done, then we start pushing this wall toward the asymptote and recalculate that area. See if it settles down to a number. In that case, we have a convergent integral. Otherwise, we have a divergent integral. So our story is going to go like this. I start from b and go to 1. Of exactly the same thing. Well, this is again a straightforward integral. So b to 1 of x to power of, what's the exponent? Minus 1/2 dx. How do we integrate it? Well, we just went through that basic formula. We have, in simplest cases, just the power formula applies. And so I'll do what? I increase the exponent by 1 and then divide by the same. And then I have to calculate it from b to 1. let's see, this is x to the power of 1/2, and this is just 1/2 also, and then this becomes 2 times x to the power of 1/2 from b to 1. So if when I plug 1 in this thing, it becomes 2. Let me rewrite this thing so it's readable. From b to 1, so it becomes 2 times the square root of, well, square root of 1 is just 1, and minus 2 square root of b. Well, that's obviously 2 minus 2 square root of b. So if I stop at b, my area is going to be this. What if b tends towards 0? Well, square root of 0 will be 0, and I'll be left with just the 2. So in this case, the integral becomes limit of this expression 2 minus 2 square root of b as b goes to 0. Well, as b goes to 0, this is 0, and I'm left with just the 2. So the area is finite, is in fact 2, and we also label this situation as convergent because we ended up with a finite number. Well, what's the opposite of that? Opposite of that, again, very famous case, the following: integral from 0 to 1 of 1 over x dx. So the previous one was radical. Radical was helping us to get a convergent designation. How about this? This is in fact a very famous and very important case. It is the case of the hyperbola. You remember the graph of y equal to 1 over x. This y equal to 1 over x, very, very important graph. It's called hyperbola. Many applications, GPS devices and so on. So what are we after? Well, we are curious. The area from 0 to 1, what is this? It turns out it's going to be infinite. Why is that? Well, let's be quick here. It's going to be limit of integral from b to 1 of 1 over x dx. When b is pushed towards 0, we stop somewhere here. Let's call this thing b, and then send b go towards 0. We are always on the positive side to indicate that. You say b going to 0 positive means we are always hovering on the right side of this. We are on the right side of history, if you wish. Then, well, 1 over x, that's very easy. 1 over x is just logarithm of x. We are calculating from b to 1, and then we are letting b go to 0. Well, what is this? Limit of, I plug 1 for x, that's just logarithm of 1. I plug b in this thing, so it's going to be logarithm of b. Again, b is going to 0. Well, logarithm of 1 is 0, so that's nuisance factor is out. I have limit of minus logarithm of b as b goes to 0. Do you remember from pre-calculus or calculus what that thing is? Think about it, try to remind yourself, maybe go dig and look at your pre-calculus book, maybe Wikipedia and such. Try to remind yourself. Okay, every one of these problems that come up is a chance for you to remember all the stuff from calculus 1 for this thing to make sense. So do yourself a favor, go ahead and review some stuff that you need, and then come back. That's the only way to be able to enjoy this. Well, logarithm, let me remind you again, we just did the picture up there. It's just a repeat of that picture. Let me show you that we actually talked about it just a second ago. Here's a picture of logarithm. Okay, so I'm drawing the same thing. Here's a picture of the logarithm. In that problem, we were going toward the right. In this problem, you see, here's your b. B is marching toward 0. Well, what is happening to logarithm? So if this is b, this line is logarithm of b. Logarithm of b is tending toward minus infinity. This thing is tending toward minus infinity. It's asymptote, it's going all the way down. This is going to minus infinity. Minus infinity is going to be plus infinity. So what happened? What happened is that integral from 0 to 1 of 1 over x, the area you wanted between the y-axis and the hyperbola and any line here, this is going to be infinite. Like if you wanted to paint this, you need infinite amount of paint, as opposed to this case, if it was between this wall and 1 over radical x, we needed finite, like if you wish 2 gallons of it, but this one, no amount of paint is going to do. How's that so? Well, you need to calculus. It's not something that you can do by looking at the picture. You have to take a limit to find out. So in this case, we say 0 to anywhere 1 over x dx is divergent, or is a divergent improper integral. So the word divergent gets to be used integral in many places. It's same connotation, something that doesn't settle down to a finite number. Okay, the way to learn this topic is by doing a lot of practice. Remember, you need to go back to your calculus 1 to refresh your memory about limits and L'Hopital rule and all those examples, and I'll let you wrestle with that with your homework exercises. Okay, until the next meeting, good luck and God bless.